Okay, today we're going to continue with Unit 8 on acids and bases with Topic 3 looking at weak acid and base equilibria. So we will explain the relationship among pH and pOH and the concentrations of the species in solution of monoprotic weak acid or weak bases. So let's start with acids. Acids react with water to produce hydrogen ions. We've seen that looking throughout this unit. If an acid is weak, only a small portion will ionize. This means that the major species, the one in the highest concentration at equilibrium, will be the undissociated acid, the acid that hasn't broken apart, and then will create a small amount of product, which would be the hydrogen ion and the conjugate base. The equilibrium constant value for weak acids and bases is going to be less than 1. It is going to favor the reactant side of the dissociation equation. So if we just looked at some values for the equilibrium constant for various acids, we can put them in order from the strongest to the weakest acid based on these values. Now, when we look at the values, we want to focus on the exponent part first. Then if the exponents are the same, we'll look at the part in the front of your scientific notation. But remember, the exponent moves that decimal, and that's going to change our values by a much greater amount. So if we want the strongest of these acids, we want to have the highest K value, which means the K value with the least number of decimal places in this case. So that would be our first one. We can see we have a times 10 to the negative 7, a times 10 to the negative 10, and a times 10 to the negative 4. So the negative 4 being the HF, so hydrofluoric acid, would be our strongest out of these three. Next would be our times 10 to the negative 7, so the H2CO3, carbonic acid, that's what's in soda. And then we have HCN, hydrogen cyanide. So that would be our weakest of these three acids based on their K values. Now, thinking about what those K values mean, we can think about how these chemicals would ionize or break down. So whatever our acid is, the hydrogen with the acid creates an equilibrium when it's weak with its hydrogen ion and the conjugate base. So again, all of these are favoring this acid side, okay? We've got values less than 1. So if we want to put these same weak acids in order of the most to least ionized in water, the one that is most ionized or tries to go towards the right the most would also be our strongest acid of the group. So if we want the least ionized, that would be the same one that is the weakest. So our order of these, the strongest to weakest, is also the most ionized to the least ionized. So continuing our look at acids, it says use the following reaction to write the Ka equation. So we have a given reaction here. If we wanted to write the Ka expression, so the equilibrium constant expression for an acid, that's all the A means, we would have our products, so the H3O plus and the NO2 minus, and you could write that as H3O plus, or you can write it as just H plus. Again, those are interchangeable. NO2 minus, those would both be aqueous, which is why we would include them. Our acid would be on the bottom, the HNO2, and again, aqueous, so that's why we include it. Now, water is a liquid, so we do not include that in our expression. So there is our equilibrium expression. We have a similar one written on your equation sheet and reminds you the setup for an acid. It says percent ionization, this is a concept that comes up once in a while, is the concentration of hydrogen or hydroxide if it's a base at equilibrium divided by the concentration of the acid or base in general times 100. So if we want to know what percentage of this acid is actually ionizing, we can use the concentration of our hydrogen or hydroxide and the concentration of the whole solution, right? The part out of the whole thing. So Here's an example. What is the percent ionization of sulfurous acid, H2SO3? If the concentration of the solution is 0.65 molar, so we have that, and a pH of 3.08. Well, let's start with that pH. What can that pH help us find? Well, pH is that power of the hydrogen ion, so we know it's 3.08. We can use that to find our concentration of just our hydrogen ion, which is also the concentration of the H3O+, right? Same thing, by undoing our pH. That's 10 to the negative pH, 3.08. And we can solve that part. So putting it into our calculator, 10 to the negative 3.08. And I'm going to put it in scientific notation. We get that our concentration of hydrogen is 8.32 times 10 to the negative 4. So that's our concentration or molarity of our hydrogen ion. Well, if we want to find our percent ionization, we want to know that's the part that ionized. So that's our concentration of hydrogen, 8.32 times 10 to the negative 4. Out of the concentration of the whole solution, which was 0.65. So these are both molarities, so our molarities would cancel, and then we want to make it a percentage, so we're going to multiply by 100. So the part that ionized is our concentration of hydrogen. The whole thing would be the concentration of the whole solution times 100. So 8.32 times 10 to the negative 4 divided by 0.65. And I'm going to multiply that by 100. So that gives me, oops, sorry, I just had an error in my calculator. There we go. So that gives me it's a pretty small percentage, 0.128%. And yes, I did multiply it by the 100 already. So only 0.12, about 0.13% of this ionized. That is a very, very tiny amount of the overall solution that actually broke into its ions. So that gives you an idea of what's going on with weak bases and weak acids, is that they're not, they may be soluble, they may be able to dissolve, but they don't actually break into their ions very readily. So let's talk about what pKa is in its relation to pH. A solution of weak acid creates an equilibrium, as we saw shown on our last slide, between an unionized acid and its conjugate base. So we have, again, that weak acid creating an equilibrium. We get the hydrogen ion in small amounts, and then we get that conjugate base as well. So the equilibrium constant for this, sometimes instead of being reported as Ka, is reported as the pKa. Now we see that P in front, just like we see it in front of the pH. So it's calculated the same way as pH. It's instead of the negative log of the hydrogen, though, it's the negative log of the Ka value. Okay, and it's pKa. So it does a similar thing to our numbers. We get rid of those exponent scientific notation numbers, kind of simplifies things. The pH of a weak acid solution can be determined from the initial acid concentration or molarity of the solution and the pKa value. This process uses rice tables, so those are still being used here, to help solve for the concentration at equilibrium. All of this is also true for bases and what we call the pKb, so the pK, or the P of the equilibrium constant for the base. Often in calculations for bases, the hydroxide ion concentration is found and used to find pOH, which can also be used to find pH. So we kind of go in that circle of finding those different values as they relate to each other. So let's look at an example of this process. The question says, what is the pH of a 0.5 molar lactic acid at 25 degrees Celsius? And it gives us our pKa of 3.08. So it gives us a little note here. The formula of the acid often doesn't matter as they all react in the same way. So we can simplify it. You've seen me write this before as just HA is our formula of our acid, we're dissolving it in water, and we get that H3O plus and the A minus. Sometimes this is also written just that even simpler way with just the H plus and the A minus. These are interchangeable in terms of the two equations because water is a liquid and that part doesn't matter to our equilibrium anyway. So if we want to solve this, what we're going to really need in terms of finding the pH is we need this value. We need our equilibrium value for the hydrogen ion or the hydronium ion, since those are replaceable. And then we find our pH from that. So we need to complete our ice table. We need to solve for that equilibrium concentration, and then we can find our pH. So let's look at what we do have. We know the initial concentration of our acid. So that's 0.5. We only have one sig fig here, but that's okay. We can assume we have no initial concentration of our products. Now, we don't have any other information to fill in here. So what we can use is our pKa value to help us out. We know that as this changes, we're going to subtract some of our acid. We're going to add some on the bright side. And I'm using X's because I don't know how much. And they're all following the mole ratio here. So we're just bringing down our numbers. 0.5 minus X. We've got X and X. Just like we've done in our last unit, we can write an equilibrium expression. So I'm going to go ahead and write that out. Again, this is the same one that's given on our equation sheet, H3O plus, sorry if it looks a little messy, A minus over the concentration of HA. And then we can plug in. Now we have the pKa, we don't have the Ka, but we can undo that. pKa, or if we want, sorry, the Ka value is going to be 10 to the negative pKa, so 3.08. And that is going to be, put that in my calculator. Sorry, I just need to get it in scientific notation. Okay, we got 8.32 times 10 to the negative 4. So that's where I'm going to put it on the left side. I'm going to fill in my right side. On the products, on the top I have X and X, so X times X is X squared. And then on the bottom I've got 0.5 minus X. Now, we can already see that our Ka value is relatively small. What that allows us to do is just like we did in our last unit, where we could say that, hey, my X value here is going to be so small that no matter what, this is still going to round to basically 0.5, right? So I'm going to eliminate this part off of my equation, right? We know our X value is going to be really small because we know our equilibrium constant is very small. So it's going to favor the reactants. Our X values are going to be very tiny. So we can solve from there. We multiply by 0.5 on both sides since it's in the denominator. So 0.5 times 8.32 times 10 to the negative 4. And we get 4.16 times 10 to the negative 4. That equals X squared. And then to undo our square, we're going to square root both sides, and our X value is going to equal, square root of that number is 2.03 times 10 to the negative 2. All right, so that gives us our X value. So we can go back and plug these in. We can find all of our equilibrium values. Now 0.5 minus basically 0.032, or 0.032. Oh my gosh, not 32. Excuse me. If I was to plug this X value in here and subtract it, we would basically get 0.05 or 0.5 because it's such a small number. My words are not working today. And then our X value is equal to that same value. Well, our goal here was to find a pH. So our pH is going to be equal to the negative log of the hydrogen ion, which is that X value. So negative log of 2.03 times 10 to the negative 2. And let's see what that gives us. Negative log 2.03, 10 to the negative 2. That gives us a pH of 1.7, since we've only got one real significant figure here in our numbers. Actually, we do have 3 on that pKa, so 1.69 would be our value there. So that's our pH. So we have a really low pH. We have a very acidic solution. It's a pretty concentrated, 0.5 molar is relatively concentrated compared to other solutions. So it is very acidic. It is still a weak acid though. Okay, remember pH does not determine if it's weak or strong. How it dissolves determines if it's weak or strong. So that's how we can use a rice table to help us find a pH given our pKa or our Ka value and an initial concentration. All right, so we're going to do another example. We're going to look at how to use our rice table again for another goal. This one we want to find the Kb value. So we want to find the equilibrium constant of a solution, and it says it's 0.2 molar ammonia with a pH of 10.8. So this is giving us a little more information in terms of what we can put into the rice table. And our goal is to find the Kb value. So let's just think about our Kb expression. If we were to write that for this equation, we would have NH4, so products, and we'd have OH minus over reactants, which would be NH3. Water's a liquid, we're going to leave that part out. So if we want to find the Kb value, we need all of the equilibrium concentrations of those 3 substances. Okay, well let's plug in what we do know into our table. It says it's a 0.2 molar solution of ammonia. So we know we have a 0.2 molar solution to start with, and we can assume these are 0 to start. The other thing that's given to us is our pH. Now pH can help us find our concentration of hydrogen, which is not in this equation. We have hydroxide, but it could also help us find our pOH, which could help us with our hydroxide ion. So if I wanted my pOH, since they are related, that would be 14 minus my pH. You can always use that equation. So 14 minus 10.8, we get 3.2. So that's our pOH. Now if we wanted to undo that and only get our concentration of hydroxide, we would do 10 to the negative 3.2. And that gives us 10 to the negative 3.2 gives us 6.3 times 10 to the negative 4. Okay, pretty small number, but let's just look at this if it was not in scientific notation, just to help us visualize a little bit. So we have 0.00063. That's our concentration of hydroxide. Now looking at our table, where does that fall? Well, anytime we are calculating a pH or a pOH, any of those are at equilibrium. That's in that bottom line there. So my concentration of hydroxide right now is 0.00063 at equilibrium. So that means that's how much we had to add in order for this column to be true. So that's how much is ionizing. Well, these are a 1-to-1 ratio, so I would have to have an equal amount of NH4 plus and create an equal amount of ion concentration at equilibrium. And my change over here would be subtracting that amount. Now let's just say we do that, 0.2 minus 0.00063. Well, I would have to round that to the first decimal because of my significant figures. My first decimal, or my first 2 digits are 0.19. So that rounds to 0.2. Value doesn't really change. Okay, so that's a great way of seeing why we can ignore, like in the last question, why we were able to ignore that x value, that amount we were subtracting. It's because they're so often so tiny that they don't actually affect our number when we come down to it. So if we want to find our KB value, that's our ultimate goal here, we can plug it into our KB expression that we wrote up above. So our products are both 0.00063 times itself, so I'm going to square it, and I'm going to divide by 0.2. So 0.00063 squared divided by 0.2. And I'm going to go ahead and put this number in scientific notation. We get 1.98. We only have one significant figure, so I'm going to do 2 times 10 to the negative 6th. And that is our equilibrium value. So pH can really help us, pOH can really help us in setting up a rice table because they give us an equilibrium value. Right? It gives us one of those values and then we're able to unlock the rest of the table. So when you're given a pH or a pOH, we want to think about how we can get that number into just a hydrogen or a hydroxide ion concentration like we did here and plug that into our table and solve from there. You'll need to do that anytime it's looking for that KB value, that Ka value. That's when we're going to want to fill in that whole table and not use an X. When we know we need to use X is when we're given Ka or Kb. That's a signal that we need to use X because we're solving for something else. Okay, so pulling an example from part of a released FRQ, so it says methanoic acid and gives us our equation, ionizes according to the equation below. So the College Board gave the reaction on this one and also gave the Ka value. Write the expression for the equilibrium constant Ka for the reaction. So that's our first step, part 1. And part 2, we want to calculate the pH of a 0.25 molar solution of HCOOH, the methanoic acid. So let's just do part 1 over here to save some space. So our Ka expression, we want products, so H3O plus times HCOO minus over reactants, remembering to leave out the water because it's a liquid, HCOOH on the bottom. So that's number 1, you get a point for doing that part. So for number 2, we want to calculate the pH and we're given a concentration of the solution. Now this is a weak acid, it's not on our list, so if we want to find the pH, we got to do a rice table. Okay, weak acids need rice. So that means we need to write the rice table. Well, I'm going to there's my reaction. I'm going to do my ice part down here and just think through this. We don't care about our water. If we want to find our pH, that means we need our concentration of hydrogen ion at equilibrium. We're looking for that value right there. We have 0.25 molar of our initial solution, which means it's not ionized yet, so we have nothing on the right side. And this is a great example of us being given Ka. When you're given Ka, Kb, that equilibrium constant, you have to use X in your table. So everything's 1 to 1. We subtract X here, add it on the other side. So we get X and X. And 0.25 minus X. Now again, we've got 10 to the negative 4 for our exponent. That's going to be moving that decimal over really small. So that means we can say, okay, this 0.25 minus X, that's basically 0.25. Simplifies things, make sure we get no quadratic equations, and then we can solve. So plugging into our Ka expression, we've got 1.8 times 10 to the negative 4 equals our products, which are both X, so X times X is X squared, divided by 0.25. So we're going to multiply by that 0.25 on each side so that we can isolate X. So 1.8 times 10 to the negative 4 times 0.25. I get 4.5 times 10 to the negative 5. And then we want to square root both sides to get rid of that square. Square root that answer, and we get 6.7 times 10 to the negative 3. So x is basically 0.0067. Okay, so we can see already if we plugged x in right here, it would be so small we wouldn't really get a change. It would round to 0.25, so that's a way to check that. Make sure rounding is okay. X is going to give us this value here, which is our concentration of our hydrogen or hydronium, which allows us to find our pH. So pH is the negative log of our hydrogen ion, and we can calculate that. Negative log of 0.0067, we get 2.2 as our pH. All right, still a really low pH, definitely acidic solution, but still a weak acid because it does not ionize very much. So it produces a significant amount of hydrogen ion, but doesn't ionize all the way. So these are some examples of how we can approach weak acids and weak bases, not when they're reacting with each other, just when they're dissolving. Okay, just when they're dissociating. How do we figure out their pH? How do we figure out their pOH and or their Ka or Kb value? So do some practice on this. Let me know what questions you have. Thanks, guys.